Welcome to This Explainer. Today, we're putting on our detective hats to transform what is usually a super stressful, failing lab result into a totally logical forensic investigation.
Okay, picture this nightmare scenario. You've just run a sample, the sequence finishes, and boom, a bright red fail flashes on your screen. Your result is officially out of specification, or OOS for short. Basically, it falls completely outside your established acceptance criteria. Now your heart sinks, right? Is this a massive product failure or just some weird, random lab fluke? Well, this exact moment turns your lab bench into a critical crime scene. And trust me, the clock is ticking.
So here's our investigation roadmap for This Explainer. We're going to track down the culprit through 6 phases. The initial OOS discovery, interrogating the lab, following the trail, a real-world case we call the Floating Assay, FDA Red Flags, and finally getting from root cause to CAPA.
All right, let's jump right into Section 1, the initial OS discovery. Our investigation kicks off the absolute millisecond that red fail appears. Now, before you even think about touching that beaker again, remember this: the clock is officially ticking. The FDA demands a rapid, thorough, and perfectly documented response to this. You really can't afford to waste a single second. Adopting a strict forensic mindset from this exact moment is literally how you maintain audit-ready laboratory records. It's that important.
Moving on to Section 2, interrogating the lab, also known as Phase I.
So what's really interesting about this next step is that we immediately lock down the laboratory. We actually call this the dumb moment. It's a rapid triage phase, Phase I, where we just check for immediate glaring mistakes to save everyone time. We're looking at 3 simple things. First, check the math. Did someone just accidentally move a decimal point? Second, check the equipment. Was the HPLC column actively leaking all over the place? And third, check the prep. Did the solution turn cloudy when it was supposed to be clear? For new lab analysts, this is an absolute goldmine, a simple checklist to spot common errors right out of the gate.
Now, if you do find an obvious error here, you've got to follow a strict initial documentation checklist. This saves time and keeps you compliant. You must formally document the error clearly, invalidate that failing result based on that specific hard evidence, and only then are you allowed to retest the sample.
But, what if there's no smoking gun? Well, then we move from Phase IA to Phase IB. We use this brilliant 6 M's Fishbone Framework to conduct a deep forensic audit of the lab. Let's break these down with some super easy examples. For man, was the analyst maybe untrained on the specific method? For machine, we pull and check the instrument calibration records. Methods, is the SOP confusing or ambiguous? Materials, we actively verify reagents to see if they were expired. Mother Nature, we document environmental conditions like was there crazy high humidity that ruined a powder? And finally, measurement. Did we actually use the wrong standard concentration? Doing this guarantees we collect all the necessary forensic evidence right during this initial phase.
Which brings us to Section 3, following the trail, or Phase 2.
Okay, so if the lab did everything perfectly, no math errors, good reagents, our investigation has to leave the laboratory and enter the complex world of the manufacturing plant. We meticulously review the birth of the batch, looking for process deviations across batch records, equipment, and personnel changes. We review the actual batch records to spot mixing anomalies. We check for equipment malfunctions, maybe a heater spiked randomly during granulation. And we examine personnel records to see if new operators or a messy shift change impacted the product. This is exactly how we verify root causes out there on the plant floor. As we gather all this evidence, we usually need more data. So, the totally crucial point here is understanding the strict, black and white difference between retesting and resampling. Retesting is running the exact same original material again. Resampling involves physically going out and taking a brand new sample from the batch. Resampling is highly restricted. It is really only permitted if you can prove the original sample was physically compromised.
And speaking of strict rules, there is an absolute boundary between legally testing a hypothesis versus illegally testing into compliance. Valid hypothesis testing means you are running controlled experiments just to prove a suspected error you found. Illegal compliance testing? Well, that's like rolling a pair of dice over and over and over again until you magically get double sixes, and then conveniently hiding all your previous rolls. Yeah, that practice is strictly prohibited by regulators.
Let's put this into perspective in Section 4, the Floating Assay Case.
Let's look at a real-world mystery and see how this all builds into an actual forensic case study with a narrative storytelling approach. The specific problem we faced? A routine tablet assay came back at a devastating 82%.
And as you can see, this 82% result fell woefully short of the expected 95 to 105% target limit. Honestly, this was a massive, alarming failure that required immediate detective work.
So what happened? Well, after Phase 1 confirmed we had fresh reagents and totally stable equipment, Phase 2 uncovered the true root cause, a mechanical dead spot in the powder blender that completely ruined the batch's blend homogeneity. Basically, the equipment design caused powder to sit stagnant, creating a completely non-homogeneous batch. Some tablets got way too much active ingredient, and our unlucky 82% sample got way too little. The lab result was actually perfectly valid, the batch had to be rejected, and the blender was ultimately modified. Boom! Case closed.
Now for Section 5, the judge's gavel, FDA Red Flags.
Listen, avoiding FDA warning signs is just as critical as solving the case itself. The FDA doesn't just look at what you found, they heavily scrutinize how you looked for it. For executives and managers overseeing this process, these are the top formal FDA warning letter triggers you must avoid. First, testing into compliance like we just talked about. Second, averaging OOS results with passing results. You can't just average a failing 50% with a passing 100% to claim a passing 75. That is strictly prohibited because it masks the true issue. Third is a lack of timeliness, letting investigations just stall out for 60+ days. And finally, defaulting to analyst error without irrefutable proof just to avoid rejecting a batch. Strong managerial oversight is absolutely required to prevent these bad practices.
Finally, Section 6, Root Cause to CAPA Flow. Let's map out the definitive transition from those initial lab findings straight through to factory resolution. This logical sequence proves that an OOS isn't a failure to be hidden, it's actually a vital data point that drives corrective and preventative action. Step 1, identify the OOS. Step 2, investigate the lab. That's Phase 1. Step 3, investigate manufacturing, our Phase 2. Step 4, explicitly define that root cause. And Step 5, implement your CAPA. Following this specific, logical flow ensures effective corrective actions and really builds long-term regulatory compliance.
So I want to leave you with this forensic mindset. Ask yourself, if the FDA walked into your facility tomorrow morning, how audit-ready was your team's last OOS investigation? Did you find the true root cause, or did you just blame analyst error and hope for the best? Don't fear the OOS, fear a poor investigation. Stay compliant, stay curious, and keep those specs in range.